Hi, I'm Kristen Halper.
I'm Gareth Merriman.
I'm Charlotte Ross.
And I'm Matthew Zong, and we're Team 5 of ECE 4534.
For this project, we were tasked to design 4 autonomous systems which communicate via Wi-Fi.
And the major objective of it is to design a robot that can find farm animals that are in different areas and transport them to the correct zones that we have created. And with this, our 4 major components are an arm, which we use to pick up and move the animals, the rover, which everything is mounted to and actually moves about the room, sensors which can actually detect and find the animals, and then the navigation component which will map the room to ensure it doesn't run into any obstacles. And so now we can move on into our integrated demo. We are storing LiDAR data. Creating a grid. All right, I have a map of the room, and it should move forward about 35 centimeters.
All right.
Oh, yep, you're good to go.
All right.
And I can send the ARM message now. Right, it's a grab success. It's storing data, and these are the most recent status color messages. It's creating the grid. All right, here's the grid of the room.
Nice.
And it's going to go back and to the right. All right, it's gonna stop and make another map of the room, and it should see that after the grid's made, it should see that there's a drop zone right in front of it. It should send an ARM drop message. So it's creating the grid now. And there's the grid, but it shouldn't matter as it will send a drop message. And I believe that is it. So now we're going to get into the LiDAR and navigation component for the system. As a general overview of how it functions, there's a LiDAR sensor that is mounted to the top of the rover that gets a 360-degree scan of the room. And from this, we have a Python script that can generate a map from these points. And then with data from sensors and the rover's current state, we're able to generate commands as to what we should tell the system to do, whether or not we want the rover to move, or in some cases, we may need to send an ARM command, such as a pickup or a drop message. So for the major hardware component of the subsystem, we have the RP LiDAR A1M8. It is a small time of flight sensor that is driven by a servo that causes it to rotate. And from that, it shoots out a 5 milliwatt laser that can then record distances around and give you angles that those distances were at. And then with the UART connection to a TI board, it's able to send the data to it, and the TI board itself is then able to send these over MQTT. And to the right, you can see the points that it generates just based off of that. As you can see, there are a few points that don't seem to be accurate to the room setup. Namely, to the far right, there is a random noise point, and there are some noise points around 0, 0. But these were able to be filtered out pretty easily and didn't affect the overall behavior of the complete system. So then onto the mapping and navigation portions. From these LiDAR points, we're able to generate 2D maps of the rooms. So to the right, we have one such map. After we generate these maps, we're able to divide them into zones based on where the sensor was. So in the example to the right, the yellow are boundary points that a rover could navigate towards. The black is a scene area that the rover is allowed to move through, and blue is an unknown area that we don't have any information about, and the rover should not be able to navigate through, but should be able to navigate towards in the event that there are no objects of interest in front of it. And so lastly, we really get into the navigation states. So there's sensing, and in this state, the rover is basically getting a reading of the room and is trying to figure out what is around it. There is a limitation though, in that we don't tell the rover to make incremental rotations to see if there are any objects nearby. And this causes some problems with object detection that we found. Um, we can also be moving. In that case, we should only stop moving if we've noticed something such as a drop-off zone while we're moving. A pickup message for the event that from the sensors we receive that there's an object nearby and we need to pick it up. And then a drop message for when the rover navigates towards a drop zone and sees it within view. And that is the general overview of how the navigation and LiDAR component works.
In this section, I'll discuss the Tri-Rover autonomous component. This includes the general system architecture, manual controls through PID, and a simple API created from higher order commands. The system architecture includes both software and hardware. Obviously, we need a microcontroller, so let's start with that. This board is wired to 3 motor drivers using a UART line. We can read each motor's speed with the motor encoder through SPI. Finally, to message between components, we pass JSON packets through an MQTT broker. We'll also need dedicated firmware for both the drivers and encoders. We feed their data into a software controller, which reports diagnostic data through Wi-Fi. A navigation translator also converts inbound Wi-Fi messages into a queue of commands which the software controller can execute. Our first development objective is to create manual controls with the PID controller. Let's take a look at how it works. Fundamentally, our manual controls must rotate the motors at a user-controlled speed. To do this, we start with the software controller generating UART motor driver commands. You'd think we're done, but because the output motor speed might be slightly inaccurate, we also need a self-correcting feedback loop. In reality, we use encoders to measure the motor speeds. The error between desired and actual speeds is what we really send to the software controller. The software controller uses PID internally. We use calibrated proportions of the error and its integral to determine the proper UART command to send. You can see the controller's oscillatory motion in this clip. Notice that the controller keeps correcting each motor's speed as the integral error changes. Now that each motor rotates properly, we can create commands that the rover can use. These commands include forwards, strafing, and rotations. The rover can buffer any number of commands at once. The rover also has a stop command. Sending it will instantly halt the rover and discard all unexecuted commands. Finally, here's a simple example of the rover in action, navigating an open space.
Moving on to the robotic arm component, The main responsibilities of the robotic arm were to locate and pick up blocks, to hold them, to drop them, and to communicate the arm's status with the sensor navigation components. The hardware used in this component was the ARM Uno 2.0 robotic arm. It had 4 degrees of freedom, the SG90 servos so that the arm could move in the 4 directions, and these servos had a period of 20 milliseconds, and the duty cycle that we sent had to go between 1,000 and 2,000 microseconds to change the angle between 0 and 180 degrees. We also had a US 100 ultrasonic distance sensor that we communicated with via UART, so we had to send it a specific 1 byte value, and it would send back 2 bytes of data that could be converted into a distance in millimeters. And all of these were connected to the TI board, and the 5-volt power supply was used to power the servos. For the software in this component, there were 6 main tasks used. So 2 of the tasks were dedicated to MQTT communications, another 2 were dedicated to the ultrasonic distance sensor setup, so making sure that it was pulled every few seconds with a timer and then sending the distance sensor values to a queue for the ARM FSM, which was the main logic of the component. So this would take the inputs from the sensor and from the other components via MQTT and make decisions about whether the arm should go out to a certain angle and scan for an object, and if it finds it, to pick it up and hold it and wait for the drop signal from navigation. And then finally, the ARM PWM task would take 4 angles and convert that into the proper duty cycle so we could update the PWM signal sent to the servos. As far as reliability and robustness, there were some issues with the robustness of the ultrasonic sensor since it didn't work with all materials, and the servos were also not the most reliable because sending the same duty cycle twice to the servos wouldn't always result in the same exact position. The main problem was with the block grabbing mechanism. So you can see here in the photo, there's actually a little bit of a foam handle because the blocks are too big for the arm to be grabbed just by the arm itself. But as you can see in this video, combined errors with the sensor and the servos and the block handle would sometimes cause the arm to not detect an object or to detect it in an incorrect position. So you see here that it saw the corner of the block, but the claw is too far back to reach the handle. But one way we worked around this was by, if the arm failed, sending it a signal to try again. And you can see here on the second time that it did indeed see the block at the farther distance and was able to successfully pick it up.
I will be covering the sensors and PixieCam. The responsibility of the sensors and PixieCam are to detect blocks and zones, to detect and avoid obstacles, verify things picked up by the arm, and constantly communicate the data with the rest of the system. The system includes the Sharp IR sensor, the color sensor, the PixieCam 2, and the TI board provided by the class. The design was implemented using a task for each sensor to take in raw data and convert it to usable data. This translated information was then interpreted by a sensor FSM. This FSM task outputted status updates for the other components to use. Status object was used for identifying objects and zones. It reports the largest bounding box it sees in front of it in the field of view. As you can see, it is identifying a cyan zone around a foot away to its right. Whenever the arm sent a grab success message, status color was published to report the color of the object that was held in front of it. This was to verify that the right object was grabbed by the arm. Right now, it is reporting a red object that we identify as a cow. Finally, a stop status was sent if there was an object within 30 centimeters of the rover. This ensures proper safety precautions are taken around obstacles that the LiDAR might have missed. Right now it's telling the rover to stop because there is an obstacle around 27 centimeters away. Overall, the only problems of the system were how the lighting affected the sensor data. In different lighting, the PixieCam would not be able to detect the right colors if it did detect anything at all. Also, the way the color sensor was mounted, it would sometimes block the light needed to read the frequency to determine what color was actually in front of it. If there was proper lighting, the system would be very reliable. These photos are from a well-lit environment that the Pixie can correctly identify all the objects in front of it. but because the system needs to be recalibrated every time the lighting changes, the design is not considered robust.